Hello. In this short video, we're going to take a look at the three-dimensional quantum harmonic oscillator. In fact, the moral of the story is that it's really no more difficult than the one-dimensional quantum harmonic oscillator, and I'm going to assume the familiarity with the results of that case and work quite quickly through this example. So the potential in this case is as follows, which equals half m omega squared x operator squared plus y operator squared plus z operator squared. The most convenient way to solve it is again using raising and lowering operators, but this time you need to define a different raising and lowering operator for each of the three directions, which are perpendicular. So we have the raising operator in the x direction is given by this expression, square root m omega over 2h bar, multiplying the x operator minus I over m omega px, where in the position basis this is as follows, where partial subscript x, again, as usual, means d by dx while holding y, z, and in this case time, all constant. So we have the same raising and lowering operators, and we have the same for, well, the etc here means same for y and z. We can define the number operator in each direction, and so we can rewrite the Hamiltonian as the sum of three terms, the nx operator plus the ny operator plus the nz operator, and then we get plus half times the identity operator for each of these, so plus 3 over 2 identity operator in total. So the time-independent Schrödinger equation reads, that is the number operator acting on the respective state returns the integer number in exactly the same way that it would in the one-dimensional case. The fact that we've been able to write states like this, labelled by nx, ny, and nz, means that nx, ny, and nz must be individually good quantum numbers. That is, we can define all three at the same time. We can have simultaneous knowledge. And just as we saw in the three-dimensional infinite potential world, this is true. The equation is once again separable, where we can write the following for the Hamiltonian. That is, the Hamiltonian can be written as the sum of three terms, where this term only acts on the x direction, so the variable x, this one only acts on y, and this one only acts on z. And for example, the hx operator is the momentum in the x direction squared over 2m, where this is defined up here, plus half m omega squared x operator squared, and then the etc indicates that we get the same for y and z, but this would then be the y operator and z operator. Okay, thank you for your time.